Morning, everybody. This is a recording of our first Algebra 1 lesson for Algebra 1B out of our Springboard book at St. Anne High School. So make sure you turn to page 3 in your Springboard book and we'll go ahead and get started here. First thing I want to point out to you guys is that you should have done the warm-up before coming to this video. Make sure that you've done that already. If you haven't, go ahead and go back and redo the warm-up. If not, here are the answers. I want you to compare your answers to mine. I'll give you a couple seconds here. And let's go ahead and get started. Okay, so on the top of page 3, we're talking about identifying patterns in a set of numbers, like a table that we see here at the top of page 3, using tables, graphs, and expressions to model situations and to use algebraic expressions to make predictions. Okay, I'll tell you what that means when we get there later in this lesson. So if you look at page 3, top of page 3 says, Meising spent his summer vacation traveling cross-country with his family. Their first stop was Yellowstone National Park in Wyoming and Montana. It's a beautiful place if you've ever been there. Yellowstone is famous for its geysers, especially one commonly referred to as Old Faithful. A geyser is a spring that erupts intermittently, forcing a fountain of hot water and steam from a hole in the ground. Old Faithful can have particularly long and fairly predictable eruptions. As a matter of fact, park rangers have observed the geyser over many years and have developed patterns they use to predict the timing of the next eruption. Park rangers have recorded the information in the table below. The next slide, that table is still there. Describe any patterns you see in the table. Okay, well, if you look at the left side of the column here, left side of the table, it says length of eruption in minutes. Okay, so you have 1, 2, 3, 4. So if an eruption lasts 1 minute, you have to wait 46 minutes for the next eruption. If it's 2 minutes long, you have to wait another 58 minutes. 3 minutes, you have to wait 70 minutes. And then 4-minute eruption means you have to wait 82 minutes. So really right here, it's kind of a bland sequence. You're just adding one over to the other. But if you look at the right side here, 46, 58, 70, and 82, the way we could look at this is a couple things. First of all, if you look at each of these numbers here, 46, 58, 70, 82, you'll notice that they keep increasing. Okay? And more specifically, if we kind of do a little bit of math here, we're saying that to get from 46 to 58, we have to add 12. 58 to 70, we have to add 12 as well. And then 70 to 82, we have to add 12 as well. So really the biggest pattern is that the right column, so the right column increases by 12. Okay, and that's as the left column increases by 1. So every 1 minute of eruption, every 1 minute increment of additional eruption time means that we have to wait an additional 12 minutes to the next eruption. Okay, why might it be important for park rangers to predict the timing of Old Faithful's eruptions? Well, like we said, it's a geyser. It spits out very hot water. So mostly this is for safety. Okay, it's for safety. Thousands and millions of people come there every year, so we want to be able to see Old Faithful. We're not going to deprive people of seeing that, but it's more so that way they can observe from a safe distance. And then looking at number 3, if an eruption lasts 8 minutes, about how long must park visitors wait to see the next eruption? Okay, so we could do this. We know that the pattern here is that we keep going up by 12. We can add 12, we can add 12, we can add 12. Okay, so if we keep up that pattern up to the point where we get to 8, what we should find is that we eventually keep adding 12 to the point where we get to 130. So 130 minutes. Okay, and I'll show you how we get there. Okay, in the next few slides. So looking at the next part right here, number 4. It says graph the data from the table on the grid below. Okay, so one thing you want to remember too is that because we have the x-axis right here, this is our x-axis, our horizontal axis, and then we have our y-axis going vertical here, we want to be able to use our data from the table respectively like this. So we have, here's our x data, here's our y data. That means we're going to be using our we're going to write these as ordered pairs. So the first ordered pair we want to graph is 146. Next one would be 258. Next ordered pair would be 370, and then 482. Okay, I'm going to graph those points for you right here. So 146 is about, I would say right here, maybe a little bit higher than halfway between 40 and 50. 258, so just below 60 here. Okay. 370, that's a little bit easier to find because we know that 70 is going to be right here. And then 482, just a slightly above 80 right there. Okay. Now, if you notice, looking at these points here, you'll notice that because we know that the right-hand column increases by 12, we can safely assume that if we were to put a line through these points, if we were to connect these points, we notice that, oops, that's not what I wanted to do. That was kind of cool though. We're going to see that these create a straight line. Okay, not going to be perfect, but about that. So we call this a linear pattern. It's linear because we keep adding the same number for every additional length of an eruption for every minute. That means we have to wait an additional 12 minutes for however long that eruption is. Okay? So looking at the next page, number 5. Okay, oops, that's the wrong slide. That's number 10. Where's number 5? There's number 5. Okay, so Myers and his family just arrived at Old Faithful to find a sign indicating that they had just missed an eruption, and that would be approximately 2 hours before the next one. How long was the eruption that they missed? Explain how you determined your answer. Okay. Now remember, we're measuring everything in minutes here. Okay. So one thing we want to do is help ourselves out. We want to convert this 2 hours to be 120 minutes instead of 2 hours, because that's going to help us in the long run. So they're waiting 2 hours, 120 minutes for the next eruption. Okay, so they're basically saying, okay, if we know how long we have to wait, how long was the eruption that they just missed? One thing we can do is if we go back to our graph, I'm going to highlight this 120 right here. I'm going to use this letter right here, or this yellow right here. I'm going to highlight this, and I want you to notice something. This value right here, that line that I just highlighted, that intersects with our graph, with that red line we just drew. Okay, and the location of it, if you're looking at it, just right here, this region right here. Once again, we didn't really use a ruler there, but in that region right there, we would say that about, looking at the graph, just kind of eyeballing it, so to say, we would say that right here, because that's where 120 and our and our line meet, we would say that it would take them, they would have to be waiting about, so Meising would wait about 6 to 7 minutes. We're going to find out exactly how long he would be waiting in a few problems here, okay? So patterns like we've seen already can be written as sequences, okay? If you look down to the right here, a sequence is a list of numbers, and each number in that list is called a term of that sequence. So 2, 4, 6, 8, and so on. With those ellipses right there, that means it keeps going on forever. That means that the terms that's listed there, as well as the terms after that, we can assume that if they follow that pattern, those are all terms in that sequence. Same thing for the next one, 2, 5, 10, 17. These are also, that's also a sequence, okay? So using the table or graph above, write the approximate wait times until the next Old Faithful eruption has a sequence. So that means we're going to start with 46, and then remember, the next term in that, if you look at our table, will be 58, and then 70, and then 82. Okay, and that's what we know so far. How would you describe the sequence of numbers? Once again, what are we doing from one term to the next? How could we keep this going if we were to look at it as a sequence that repeats, or not repeats, but keeps going by adding 12? That means that we would just say we start at 46 and then add 12. Okay? So that's one way to describe it, starting at 46, keep adding 12, and that's how we would move forward from there. That's one way to describe that sequence. All right, looking at number 8 on the next page here. Okay, so number 8 at the top of page 5 here. We're given another box here. It says in the table below, 5 and 8 are consecutive terms. Some sequences have a common difference between consecutive terms. The common difference between the terms in the table below is 3. That's because we're looking at 5, 8, 11, and 14. So to get from one term to the next, we have to add 3. So that means that our common difference, that's how we know what a common difference is. If we add or subtract a number to get from one term to the next in terms of its consecutive terms, that means that that's what our common difference is, to get from one term to the term after that, and the term after that, and the term after that. So 2 consecutive terms in the sequence of next eruption times for number 8 that you created in item 6. Well, consecutive terms, that would be, if we started at 46, the term after that would be 58. But if we wanted to look at 58 as well, we could also have 70. So 58 and 70 would also be considered consecutive terms. And then 70 and 82 would also be a set of consecutive terms. The sequence of the next eruption time has a common difference. Identify that common difference. Well, what are we adding every time we go up and down our table in the eruption times? We're going up by 12. So that means that our common difference is going to be that number, which is going to be positive 12. Okay? So once again, the common difference is the number that we add or subtract in a sequence to get from one term to the next, to the next, to the next, and so on. Okay? Looking at number 10, bottom half of page 5. Number 10, each term in the sequence above the new one can be written as using the first term. Okay, that's important. The first term and repeated addition of the common difference. That's important. We'll talk about why this is important in a little bit here. For example, the first term is 5. The second term is 5 plus 3. Okay, so once again, first term is 5. That common difference comes up again. There it is. And the third term can be expressed as 5 plus 3 plus 3, or 5 plus 2 times 3. Okay, similarly, terms in the sequence of next eruption times can also be written using repeated addition of the common difference. Right, the approximate waiting times in part A for the next eruption after eruptions lasting 4 and 5 minutes using repeated addition of the common difference. So basically they want us to rewrite everything we've seen with the geyser problem using the method they have for number 10 here. Okay, so once again, we write the first term for, let's do 4 minutes really quick here. 4 minutes, or we write 46, that's our first term in that sequence. And then we add how many times we would have to go, or how many times we would have to add our common difference to get to 4. So that means, so if this is our first term, that means we would have to add 12 here. That's my second term. Oops. Second term. And then we add 12 again. That gives me my third term. And then we'd add 12 again. That gives me my fourth term. Okay? So that's how we write it out. And that should give us, if we do 46 plus 12 plus 12, that should give us that 82. Okay? Double check my math for me, but that is how that should work. All right? Same thing goes for 5 here. Okay? We start with our first term, 46, and we add our first term, and we add 12 until we get to our fifth term here. So let's see here. So 12, that's our third term, plus 12, that's our fourth term, and then there's 12 again for our fifth term. Okay, now we know that this part right here, this is equivalent to 82. So 82 plus 82 plus 12 is going to give me the next term, which is going to be 94. Okay, so here's the important thing that I want to point out to you guys really quick here. Notice how many times we had to add 12 for 4 minutes. Okay, for 4 minutes we had to add 12 3 times. Okay, that's important for part B. It says model with mathematics. Let n represent the number of minutes an eruption lasts. Write an expression using the variable n that could be used to determine the waiting time until the next eruption. Okay, so in terms of the repeated addition that we've seen here, we want to be able to say if we're looking at n terms here, so an unknown number of terms, we're going to write an expression. So if you look at the top right here, it says an expression may consist of numbers, variables, and operations. Okay, so we're going to have to write something with the variable n representing the number of minutes that an eruption lasts. Now really quick here, looking at part A. For 4 minutes, once again, we had to write plus 12 3 times. So there's a difference of 1 here. So we have to take 1 away from the number of minutes that we're looking at. So in this case, once again, we start with our first term, which is 46. We add our common difference, but now we want to multiply by a number, n, to represent how many minutes there are, but we have to take 1 of those away. There's always a difference of 1. So it has to be 46 plus 12 times n minus 1. And once again, we're using that table that we've seen already. Check the accuracy of the expression by evaluating it when n is equal to 2. So that means we're going to have 46 plus 12 times 2 minus 1. 2 minus 1 is equal to 1, so 12 times 1 is 12. So 46 plus 12 times 1 gives me 46 plus 12, which is 58. And if we look back at our table, once this works, once it catches up with ourselves, we see, yeah, we get 58 right here. 46 plus 12 definitely gives me 58, okay? Now, once again, we could keep adding 12 over and over and over again, but eventually we run out of patience, we run out of time, and we don't want to keep adding 12 multiple times, especially if we have an eruption that lasts, let's say, 20 minutes. We could do it, but it's not time effective. Using this expression here, we can save ourselves some time, and we can predict how long we'd have to wait if there was a 12-minute eruption. And all we have to do is, okay, so if we're looking at 12 minutes, that means that our variable for n has to equal 12. So 46 plus 12 times 12 minus 1, that's going to give me 46 plus 12 times 11, because 12 minus 1 is 11. 11 times 12 is 132. So 46 plus 132, that's going to give me 178. So nearly 3 hours of waiting until the next eruption after a 12-minute one has just gone off. Okay? Taking a look at the check your understanding at the top of page 6 right here. Go ahead and try these out on your own, and we'll check your answers really quick here. All right, number 11. Check your understanding. It says SB Mobile charges $20 for each gigabyte of data used on its smartphone plans. Copy and complete the table below. Table showing the charges for data based on the number of gigabytes used. Okay, so if it's $20 for every gigabyte, that would be for 1 gigabyte. Then they charge me 20. For 2 gigabytes, they charge me 40. For 3, they're charging me 60. For 4, they charge me 80. And for 5, they charge me 100. Okay, seems to make pretty good sense here. Okay, write a graph or graph the data from the table. Okay, you guys can do that on your own. I'll let you do that. But what I would suggest is if you're doing a graph, you guys have the graph paper, I do not. Here's what I would do: make this X, so this is your horizontal graph. Make this Y, so that's your vertical here. And keep it simple. So you'd have 1, 2, 3, 4, 5, 6 like this. So 1, 2, 3, 4, 5, 6. And then make every one of these hash marks worth, I would say 20. Keep it simple. So 20, 40, 60, 80, 100, 120. And you can keep going. You have more space than I do on the margins here. But the graph should look something like this. So for 1 and 20, 2 and 40, 3 and 60, 4 and 80, and then 5 and 100. Once again, if you're using the graph paper that's in the margins for you guys, you should have kind of the same sort of deal. We're adding 20 every time. That gives us a straight line. Okay, so number 13, I'm going to use green here. Write a sequence to represent the total price of a data plan. Okay, so that would be 20, 40, 60, 80, 100, and we could keep going as well, but that's what we're given for the table here. The sequence you wrote in item 13 has a common difference. Identify the common difference. Well, what are we adding every time? We're adding how much each gigabyte additional gigabyte of data costs us, so that's going to be 20. Let n represent the number of gigabytes used. Write an expression that can be used to determine the total data charge for the phone plan. Okay, so that means we start with the first term, which is 20. We add on our common difference, which is also 20. Now we have to think of it as, okay, we already got the first term covered, so we need to have n take away that first term. So 20 plus 20 times n minus 1. Now, some of you may have written 20n to represent that. If you have either one of these, you are correct. Let me show you why. If we take this 20 here and distribute it, which means we multiply here, we get 20 plus 20n minus 20. Well, now that we've distributed, we have to combine our like terms, which are this 20 here, this 20 there. So 20 take away 20 is 0. That means we are left with 20n. So if you wrote either one, the long way like we saw in the lesson, or if you wrote, hey, wait a minute, all I'm doing is multiplying by 20, then absolutely, you are correct here. Okay? You don't have to distribute every time, but if you want to, absolutely, that is one way that you can do that. Use your expression to calculate the total data charge if 10 gigabytes of data are used. Well, that's just 20 times 10, which is $200. Okay? So, well, if this would look more like a 0, that would be helpful. All right, so your homework for this lesson is to do, once I find it on here, this page 7, lesson 1.1 practice. All right, make sure you have that done. Make sure you're asking questions, and I will see you guys later.